We're going to start chapter 5 today, and we're going to look at the area under a curve and how we can use calculus to help us figure this out. And then ultimately, what is the application of this? Why are we interested in this information? So make sure your cell phone is put away and you're ready to pay attention for the next few minutes and you're taking notes in your course packet. I'm starting off with an example here looking at the function x squared plus 1. And I'm only looking at the first quadrant. And what I'm interested in is thinking about how can I find the area underneath this curve from 0 to 4. And don't write this in, but I just want to show you specifically what it is that I'm talking about here. The area of interest would be from x equals 0 to x equals 4. And I'm interested in this region in the first quadrant bounded by the function and the x-axis. And if this were like a straight line function, we could maybe use geometry to help us figure this out. But the problem is that this function is curved. And so that's where the calculus comes in. One option would be to break this into figures that we are familiar with, like rectangles. Perhaps we could subdivide this and say, all right, let's subdivide this into 4 rectangles and say we draw the first rectangle at the left endpoint where x is 0 up to where it hits the curve, and then the next rectangle where x is 1 and that hits the curve, and then where x is 2, and then possibly where x is 3. So this gives us an approximation for the area, but you can see that this would be an under approximation. How could I perhaps make this a little bit more accurate? Maybe instead of doing 4 rectangles, we subdivide it a little smaller and we do 8 rectangles. So if we do 8 rectangles, we could draw them the same way at the left endpoint where each left endpoint hits the curve and goes over. So we go up and over, up and over. And hopefully you see that this gives us a slightly better approximation because now there is less remaining area outside of those rectangles but underneath the curve in blue. How could we make this approximation better? Could we use more rectangles? Maybe instead of 8 rectangles, we break it into 16 rectangles and get another approximation that way. Well, let's look at Desmos and see what this looks like using technology, because of course my picture is not doing justice to it. So let's take a look at Desmos. All right, I'm looking at the same function here, y equals x squared plus 1. So I'm looking at the parabola from 0 to 4. And I'm starting off with drawing those rectangles at the left endpoint, and I'm going to start with 4 rectangles. So you can see that the first rectangle, the endpoint, the height would be where x is 0. And then the next rectangle, the height would be where x is 4. I'm sorry, where x is 1. And then the next rectangle, the height was drawn where x is 2. And then the next rectangle, the height was drawn where x is 3. So this is what we would call a left-handed approximation because each of the 4 rectangles, we drew the heights at the left side of that particular interval. And notice the right endpoint of 4 got left off. Well, this is with 4 rectangles. Let's try using 8 rectangles. And as you saw earlier, this gives me a slightly better approximation. Could we make this a little bit better? Well, let's try 16 rectangles. There we go. We get a little bit better approximation. And I can actually increase the number of rectangles all day long here. In fact, I could go all the way to infinity, and that would give me the exact area underneath the curve. Let's go back to the notes for a moment and look at the next example, and we'll come back to Desmos here. It says, approximate the area under the curve on the interval 0 to 2. How many rectangles should we use? Well, that's up to you a little bit. Most of the time in a question like this, they'll tell you to approximate this area using a certain number of rectangles. I'm gonna go with 4 rectangles here, and let's think about what the width of each of those rectangles would be. So the width you can always think of, if this is A and this is B, and that's my interval that I'm working with, it can always think of it as B minus A divided by N. So let's say if we use 4 rectangles, then the width, or the delta X, I'm going to call it, so we'll call it delta X for the width, would be 2 minus 0 divided by 4, or 1/2, or 0.5, however you want to write it. So I'm going to try to draw this as best I can on this graph. We're looking at the function just x squared. So there's 0.5, and here is 1.5, and of course 2 is here. All right, so if we were to do a left-handed approximation, that means that I'm going to start at the far left endpoint. So I'm going to start out at 0, and notice that this curve goes through the origin. So the first rectangle, the height is actually just 0. It doesn't go anywhere because it actually goes through 0 on the graph. In other words, the corresponding y value there is 0. So the area of a rectangle, just in general, remember, is length times width. So if I'm doing a left-handed approximation, my first rectangle has a width of 0.5 and a height, or a length, of 0. My second rectangle I would draw at 0.5 and cut over. So that would be a width of 0.5. And how would I get the corresponding height right there? Well, I need the y value when x is 0.5. So that would be, because remember the function was x squared, that would be 0.5 squared. Plus the next rectangle, we would go up at the left endpoint of 1 and cut over. So my height, or my width rather, would be 0.5, and this time my height would be where x is 1. So that would be the corresponding y value when x is 1. That's f of 1. And then the last rectangle would be 0.5, and I would draw the width, or the height rather, at 1.5 and then cut over. There we go. So that would be at f of 1.5, which would be at 1.5 squared. So when we put all of those together, let's see what that gives us for a total. When I simplify all this, I'm getting a left-handed approximation of 1.75. And I want you to see in Desmos what that looks like, and that Desmos got the same number. So here is the function x squared in Desmos, and I'm only interested in the interval from 0 to 2, and I have 4 rectangles drawn at the left endpoints. Make sure you see that the y values, or the heights for each of those rectangles, is where that left endpoint gets substituted into the function x squared, and that's what those heights are coming from. And Desmos right here, here's the number, and that would be 1.75. That's the approximation we got, okay? And we only used 4 rectangles, but we certainly could have used more. This looks to me, let me slide this over, this looks like 30 rectangles, and you can see the approximation changes to 2.53. We could raise this. There's, looks like 37 rectangles. We go all the way to 100 rectangles. My approximation becomes 2.62. And hopefully you see that the more rectangles we have, the better this area fits right into the curve. We have less of that, that space between the rectangles and the curve itself. Now let's go back to our notes for 1 second. This was a left Riemann sum. That's the special name for this, is a Riemann sum. So you'll hear me say that from time to time. Let's talk about what a right Riemann sum would have looked like. Now, in your notes, I should have given you a better graph of this, but in your notes, I'm going to go ahead, I'm going to erase what I have here, and I'm going to draw the rectangles for what's called a right Riemann sum, so you can see the distinction. We're still going to use widths of 0.5, so I think 1 was maybe like right here, so 0.5 would go here, and 1.5 would go here. And the idea is, instead of starting at the left endpoint at 0, I'm going to start in that first interval between 0 and 0.5. I'm going to start at 0.5. So I'm going to go up to the curve, and I'm going to cut over that way. So the first rectangle, let me make a little bit of space here. So this one was 1.75. Let's leave that in our mind. I'm going to come down here and I'm going to say the right Riemann sum, so A sub r. The width is 0.5, and the height is going to be 0.5 squared. So in other words, it's the corresponding y value at 0.5 right there. Then I'm going to draw it at 1, and I'm going to hit the curve and cut over. So that would be 0.5 times 1 squared. Plus the next rectangle, I'm going to draw it at 1.5, and I'm going to cut over. So that would be the value at 1.5. So that would be 0.5 times 1.5 squared. And then at 2, I'm going to draw the last one and cut over at 2. So at f of 2, that would be 0.5 times 2 squared. And let's see what that gives. So this gives me a right approximation of 3.75. And this should make a little bit of sense because, so this was our left and this was our right. This should make a little bit of sense because this is an over approximation. Notice that these are outside of the curve, so they over approximate it. And if we go back to Desmos for just a quick second, this will actually, Desmos will do this for us. If we change this to a right Riemann sum, and let me change this back to 4 rectangles, there's my graph. So you can see the first rectangle was drawn where x was 0.5, and then where x was 1, and then 1.5, and then 2, and so forth. And you can see 3.75 is the approximation Desmos got. Again, if we increase the number of rectangles, you can see pretty clearly that this gives us a better and better approximation. So the more rectangles we can include, the more accurate our approximation is going to end up. A couple of other little vocabulary terms I just want you to be familiar with. Inscribed rectangles, you might hear that term. Those are all drawn below the curve, whereas circumscribed rectangles are all drawn above the curve. Whether the rectangles approximate or over approximate or under approximate depends on the behavior of the graph. And we'll get more into that later on, but I just want to kind of get your feet wet, and we'll do some practice with this tomorrow in class.